Hi, it's Scott, and I hope everybody had a great Thanksgiving. But this is my calculus Riemann Sum project.
For Thanksgiving this year.
We had to travel from one destination to another by car and record the velocities of the car after certain durations of minutes. In doing so, our ultimate goal was to closely approximate the actual distance that we in the car traveled. So here's my problem. So I traveled from Merrill, New Hampshire to Boston, Mass, and every 10 minutes I recorded the velocity of my car. My recorded values are shown in this table. What we first observe from this table is that the 10-minute time intervals that I said are recorded are actually recorded in hours. So for example, one 10-minute time interval is 1/6 of an hour. And the reason I made this unit conversion was so when we multiply the velocity by the time in a velocity time graph to get the area under the curve and to get their total distance traveled, we're going to be multiplying miles per hour by hours, and the hours are going to cancel out, and we're going to be left with miles. Alright, other than that unit conversion, everything else is pretty self-explanatory. And we've been doing a lot of it in class, so it should become almost second nature. So to find the left-hand Riemann sum algebraically, we're going to take the duration between each interval. So in this case, it would be 1/6. And we would multiply this for the left-hand Riemann sum by the leftmost value over each time interval. So for example, we would take 1/6 and multiply it by the sum of 27 plus 48 plus 71 plus 70 and so on and so forth. And for the right-hand Riemann sum, it would just be the opposite. We would do 1/6 times the rightmost values. So 1/6 times 48 plus 71 plus 70 plus 72. And as you can imagine, that goes on just like the left-hand sum did. Okay, now let's look at this graphically. This is a graph of the left-hand Riemann sum, which we calculated as being 115 miles last slide. So how does this 115 miles, how is it resembled in this graph? Well, that 115 miles comes from each one of the area of each one of the blue bars all added together. So the entire area of this graph is equal to 115 miles if you added them up. And likewise, now looking at the right-hand Riemann sum, if you find the area of every single one of these blue bars and add them together, you should get 116 miles, exactly what we got a couple slides back. And if you don't believe me, go ahead and try this on your own. Find the area of every single one of those blue bars and add them together. And take my word for this, you're going to get 116 miles. Okay, now once we've calculated both the left-hand and the right-hand Riemann sums, all we have to do to find the best possible approximation for the data that we have is average the two together. And what we're going to get is that my car traveled 115.5 miles. Now this is the best approximation that we can make with the data, but it is not entirely accurate. This should be pretty clear with the odometer readings that I took before and after the trip. The odometer read that the actual distance of the trip was 112 miles, only 3.5 miles off the Riemann sum approximation. That the Riemann sum bar is closed this time, I'll explain later why it is not a reliable method for solving this problem. Okay, now back to the actual accuracy of our Riemann sum. So our Riemann sum came less than 4 miles off the actual distance of the trip with less than a 4% error. Now this is really, really good. So was our experimental data good or was it lucky? And I'm going to propose that this was lucky, because what this means is that our average speed over a given interval was very, very close to the speed which we recorded over the same interval. Now, this is not always going to be true, which is why it's lucky. Okay, so say you're in Boston and there's a lot of traffic, and you're going on the highway, and for 9 straight minutes, you're stopped. And then on the 10th minute, you're accelerating at 60 miles an hour. So you record the 60 miles an hour in your data, even though your average speed is only 6 miles an hour. Now this is going to skew your data and ruin your Riemann sum results. So now you're probably wondering, how can we improve our approximation? Well, to improve our approximation, we're going to have to make the intervals of time between recording the velocities smaller and smaller. And by doing this, we're making the average speed of the car closer and closer to the speed which we record in our data. By doing this, our results are going to be closer and closer to the actual distance traveled by the car. Okay, now the last slide is just a fun fact. It's just applying the average value theorem to this problem. And for this problem, what the average value theorem is finding is the average speed of my vehicle over the entire trip. And how we do this to find the average value is we take the integral from a to b and divide it by the change in x. In this case, our integral from a to b is just our Riemann sum, and our change in x is the total time I traveled, which is 1.83 hours. And what we're going to get is that the average speed of my car was 63.11 miles per hour. And I want to thank everybody for watching, and more importantly, I hope you had a great Thanksgiving.